So you have an isolated spherical planet. Isolated means what? No other planet nearby, no field, no force, no potential, just one planet. Hey, they never give diagram, oh. This chapter, if they never give diagram, you must draw. Just draw a circle, sphere planet. Okay. Pretend it's a sphere. Diameter, D, quite big. Mass, super heavy, mass M. Assume to be a point mass at the center. So assume it's sphere, so all the mass can be considered concentrated. Show that the gravitational field strength at the surface is 3.7 N per kg. Ah, how to find this one? Remember gravitational field strength we looked at last week? If you made the equation sheet, or you can already remember the main, what you call it? The main equations of this chapter, then you can remember, oh miss, G equals to Gm over R squared. If you don't remember this, hopefully you remember at least Newton's law. F equals to mg. So G equals to F over m. And what is F? F is the huge Gm over R squared divided by m. So this whole thing, cancel out the m will give you Gm over R squared. And that's what we just used here. So you either memorize the step or you know how to derive it to get there lah, for this gravitational field strength. Anyway, where were we? Okay, so we need to calculate. We plug in everything we know. If we are at the, where? Surface of the planet. Oh, only surface ah? Yeah lor, here lor, like us. So we need to know what the R is here. R. If they give us diameter, that will mean this whole width, D. That's given up here. All right, so you try quickly doodle as I also write it out. Calculate along with me if you haven't. 6.67 times 10 negative 11, that's our constant. Mass, 6.4 times 10 23 divided by radius. Just take half the diameter lah. Half diameter. Already in meters? Oh, so good. No need to convert. Very good. This one, if you calculate, you should get about 3.69 Newton per kg. You know why Newton per kg, right? Because F equals to mg. So G equals to F Newton per mass, kg. That's how you know the unit of gravitational field strength. How strong is the field at the surface? Come, we draw field line also. Ah, see the field line? Field line is roughly constant at the surface. So this is roughly constant at surface. Okay, 2 points. First one is you know the equation or not. This is equation. And you manage to submit everything and get the correct answer, show you're working, that's the final one. If you did not get to solve, then you just take their value and continue with the next part of the question. So let's see what happens next. A stone, got mass now. Let's say the mass here, inside the big M, is raised from the surface through a vertical height of 1,800 meters. Use your field strength to determine the change in GPE of the stone. Change in GPE. Delta GPE. Explain your working. Explain means you probably should say some sentence. So now we have to think of all the equations we know for GPE. The first one you might think of is, and then miss, just now we saw the GPE one. Isn't it this GPE equals to M times delta phi? Correct, but we don't know what phi is. No graph, no values, cannot use. Not enough info. Not enough info. So how? We need to use another method. Ayo. Well, let's see. They did say something important though. You see this? Use the value of G field strength in A. So somehow we need to use this 3.7. Use that to calculate change in GPE. So we have to think and like, oh wait, this is near the surface. And your change in height, maybe we can use MGH. Yeah. Can, man, miss? This chapter can use MGH. Can, under very specific conditions. What's the conditions? If you want to use MGH, number one, your G is constant or roughly constant. Is a constant 3.7 Newton per kg. So good guess if you thought of maybe we should use MGH. G is constant, number one. So I write here if G is constant and your change in height is much lesser than the radius of the planet. These two are the conditions lah. So 1800 is like barely just move up a bit. Pretty much like what you all do in AS. Oh, here got ball, the ball throw up, reach a certain height. Here got change in height, so MGH. That's only for very small distance. But if you travel away from the planet, then cannot use MGH already. Because then your G field strength is not constant, not 3.7 anymore. So now we can say yes, can. Because we know enough information otherwise. So we can calculate EP. Sometimes people use U, UE, GPE also can. Change in GPE will be MGH. So 2.4. Do not use 9.81, okay? So you say, oh, G is 9.81. Wrong planet. You need to put 3.7. Why? Because we're on a different planet. We are not on Earth. So don't 9.81. This is 3.7 times height. 1,800 meter. Actually not very high also. Go to the sky, come down a bit. Okay. Calculation. So my values 15984. Roughly, I would get a value of 1.6 if I round it off times 10 to the 4. Standard form. If you use 3.69, also can lah. You just, your decimal might be a bit different, but if you round off, it should still be about 1.6. So this is a 3 mark. Okay, 1 is probably for final. The other one comes from your explanation. Explain. Because they ask you to explain, so you must say something. And lastly, if you plug everything in the correct value, MGH sub into MGH, that's 1. Okay, only near surface where field is constant. Approximately constant. I draw the field line. Field line. Okay, moving on. If you want to see this, by the way, you can go to OneNote class board. You should be able to see it as it updates. Okay, now we have to space travel already. Okay, now to apply our new knowledge. A rock initially at rest at infinity. At rest should ring a bell, V0. Because you are resting, where you want to go? What you want to move? No energy also. So V0, maybe an asteroid or something. At infinity. Infinity tells me that the potential is 0. By definition, we define far away to be 0. Come closer and closer towards the planet. So let's draw the rock here. Super duper far away, not moving at first. Why? Where? How? Potential 0. Okay. As you move closer and closer, you will reach point P, where is a height above the surface, 3.5 D. Okay, so from very far away, we come here. Guess you could call this R equals to infinity. So they didn't give us a graph, but you can draw your own graph. It will look something like this. So you have first the middle axis, okay, so kind of align with the center. Then you have the horizontal axis that goes very far, I suppose, all the way to infinity. Okay, I don't want to draw so far. Here lah. And you have your graph, the reciprocal graph that kind of approaches 0 as you go to R infinity. Okay, approach 0 as you go infinity. So that's a phi against r graph. But you somehow from infinity you end up here, point P. What do we need to calculate? Speed of the rock at P, assuming the change in gravitational potential energy all transfer to kinetic. So from infinity, okay, like this graph, let's say we already reached infinity, approach, almost touch infinity. From infinity to the point P, there is some kind of change in gravitational potential energy related to a change in potential. How can we calculate this? Okay, here's the first tip. Imagine you're on the planet, you see this rock coming, it's basically an asteroid. If you've ever seen an asteroid, you look in the sky, suddenly, wow, something burning, getting bigger and bigger. Something is traveling from very far away from the planet, traveling towards the planet. This is what's happening. So of course, you're going to start moving faster. You start off at rest. As you approach the planet, you're going down into the potential well. Your velocity is now faster. Why? Because there's a change in energy happening of the rock. So for the rock, this is the first hint. You have firstly a change in kinetic energy. This is related to an increase. Move faster and faster, something go towards the planet. You're being attracted to the planet. There's a gravitational force pulling this object. But where the energy come from? Gravitational potential energy. If you're very far away, your potential energy is very high, 0. As you come closer, you roll into the negative potential well and you get attracted to it. So here is a change in GPE. There is loss or decrease in GPE. There, you see the graph here, GPE is very high, right? High. You roll down already here, GPE is low. Okay, now we gotta choose the equations. Okay, so for this kind of equating equation, you can use similar to what you do for AS, but the equations are a little bit different. For KE, increase, right? You just take the bigger one minus the smaller one. So when you are at this spot, you are moving pretty fast. So that's probably going to be bigger. So you can go half mv squared minus, at first, what is your kinetic? Resting, no kinetic, 0. Then we do GPE. How to find GPE? M5, can we use M5? I think we can. Let's try it out. Okay, so for GPE, we're going to use M times delta phi. Phi is potential, right? Oh yeah, we find equation lah. So half mv squared. M and M cancel out. Beautiful. Get rid of it. Don't care what the mass is. So half v squared equals to change in phi. You gotta use your negative gm over r minus negative gm over r. Which one is bigger? Which one's smaller? Here is high GPE, so we use this high one minus the low one. So this one, GPE at infinity is just 0. So we don't need to say anything about 0. 1 over infinity is 0. So let's get rid of the 1 of the gm over r. This one initial is bigger minus the final. Okay. Last line, half v squared equals to, at infinity, pretty much 0. So this whole thing is 0. At infinity, r equals to infinity. Pretty much 0. What's left is this one here. So it's just gm over r. So I'll simplify down to this. Am I missing an m? Oh, the m cancels out already. Okay. Can so far? Okay, let's calculate now. All right, plug in values. So we got half v squared. We need to find the v. G is 6.67 times 10 negative 11. Mass. Hey, the super big mass is what again? We scroll up. Mass. Mass here. The 6.4 times 10 to the 23. Super big mass. Let's write down there. So you're rolling around in this huge planet's mass. So 6.4 times 10 to the 23 divided by radius. Okay, what's the radius? This R here, radius, what we really mean is distance between the center of this circle to point P, which is where you are here. What's the distance? See this thing, oh. How to calculate? What's the distance? 4D? Sounds like the 4D Toto, you buy the lottery one. Yes, correct, it is 4D. This one is only 0.5. So the total distance here is 4D. 3.5 plus 0.5. Okay. 4 of diameter. What's the diameter? 6.8 times 10 to the 6. We're going to write that in. So back down to this. 6.8 times 10 to the 6. There. Oh, finally. Okay, can find the velocity now. So this velocity, time to press calculator. Someone also calculate with me, double check. Maybe I press wrong sometimes. 11. Okay, what y'all get for this velocity? Don't forget the square, the v square, must square root. Rounded, can we can round. Okay, so I got 1772. Okay, 171.67, blah, 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 blah. We can round it off to 1800. 2SF. Or you want to write in standard form, this will be 1.8 times 10 to the 3 meters per second. Can write like that. Rounded. Your values will be slightly different. Might be slightly different. Okay, wow, this one is 4 marks. Nani, so much. Number 1. The first mark comes if you know how to find your gravitational potential energy. So is there a GMM, where is it? GMM over R. Okay, I already cancelled out the thing, but if you know how to use your M5, this one is 1 mark. Equation. Some of you prefer to straight away use the equation for potential energy, which is just GMM over R. Also okay lah, but it basically comes from here, M times 5. Yes, write out the other step, M times GM over R, right? So you get GMM over R. You got that step. You want to jump to there also, okay. Number 2, if you equate with velocity, so that will be something like this whole line, could be anyone, where you equate. GPE decrease liao. Go to where? Go to kinetic energy. Since there's no friction or energy loss. So we have 1, 2. Number 3, if you plug in your correct values for D, for distance, this one. Use of 4D, this one is 1 mark. Must know what is the distance between center and point P. Lastly, manage to get the final, that's accuracy for the final mark. So this 1771, if you are ever an engineer or some kind of satellite, rocket, spaceship, aerospace, something, you kind of have to make sure the speed is not too fast when you are entering a planet. Because if your speed is too fast, you might have some problems. So the question people always have to ask themselves is this too fast to enter planet? The scientists and the physicists and engineers have to do careful calculations, because if you enter too fast, you might crash upon impact. Your structure just cannot lah. Your iron will break, your wire will fly out, everything. Or you come in too fast, the friction might be so big, it will burn your rocket. You know, you got see the movie, right? Something come in, then got fire. That's the fire is the heat due to friction. So make sure you do your calculations carefully if you ever want to travel space to outer space to another planet. To make sure you don't hit so fast. It's not GG. All the hard work crashed.